So this is an application of a lot of the concepts that Ben just went over, and even that Josh went over too, just sort of an application of the ecological economic concepts for thinking about energy, and to analyze nuclear energy as a option for mitigating climate change. So luckily I can go through this really fast because Damon talked about some of this stuff earlier, and so did Josh, and so did Ben. I really like the Steve Keen quote, "Labor without energy is a corpse, capital without energy is a sculpture." So can't do anything without energy. And this is sort of the current situation with energy. Humanity consumes about 12.5 terawatts continuous power if you take annual energy use and average it over a year, which isn't perfect. It actually fluctuates a little bit, but it's about 12.5 terawatts from something like 18 terawatts of primary fuels, because there's losses in efficiency in using fossil fuels especially. And this is the carbon budget stuff. So this would add up to 21 years of carbon emissions, of 36 gigatons of carbon emissions left. But that's not that helpful because during those years you have to be declining to zero, so you can't just have 21 more years of fossil fuel use and then stop. You have to, realistically, it's going to be a longer decline that needs to start sooner rather than later, because we need fossil fuels to build the new energy infrastructure, because we can't yet build it with other types of energy. So there's a need for new non-fossil fuel energy sources that are clean, abundant, cheap, safe, and dense. And I'm going to go into what all those words mean, but clean basically is low carbon, abundant is enough to replace fossil fuels, cheap is affordable enough to deploy them on a massive scale, safe is without really, really bad side effects, which, I mean, most energy sources are going to be safer than fossil fuels, luckily. And dense, it has to do with usefulness, but in this case, I'm going to talk about dense as in terms of land use by energy sources. So a lot of folks, including really famous climate scientists like James Hansen, are now suggesting that nuclear energy is the salvation. Really dark in here, for the climate, or even just the most practical option. You know, even people like George Monbiot, a journalist, kind of came around to nuclear because he said, "I'm anti-nuclear in the long run, but this is really urgent. Climate change is really urgent. Nuclear energy makes sense for right now because it can replace fossil fuels quickly," or that's the story that's told, at least. And so this comes from a big literature review, a big research project I've done evaluating with my colleague and supervisor, Yurgos Kallis, analyzing or reviewing the academic literature surrounding the claims by these folks who call themselves Eco Modernists in their manifesto and other documents they've written. So this is a quote from the Eco Modernist Manifesto, and the Eco Modernist Manifesto is an exaggerated version of a lot of the views and beliefs that sort of underlie very mainstream beliefs about fixing environmental problems with technology, but not changing social structures or economic systems. So they say that nuclear energy is zero carbon. They say that it has been demonstrated to meet most, if not all, of the energy demands of modern economy. So is nuclear energy clean, abundant, cheap, safe, and dense? I'm going to go through those somewhat quickly, hopefully. So these are different electricity generation technologies. Greenhouse gas emissions. The estimates vary wildly, and that's because of two things. One is actual differences in energy systems of the same technology. Renewable and nuclear systems, neither of them are zero carbon. It's absurd to say so, because the energy investment needed to get their energy return is from fossil fuels. You have to build things with fossil fuels, get materials out of the ground with fossil fuels, and so their carbon emissions from a life cycle perspective depend upon the energy economy within which they're embedded. And then the second reason that the estimates vary wildly is because of methods, researcher decision making, and their assumptions. So researchers can come to the conclusions that they want to come to if they so choose. And so it's hard to find. This was a harmonization of life cycle assessments. So the researchers did their best to to keep the methodologies consistent, but it's really difficult to do because there's a lot of different factors. But anyway, the one thing that we can see is that nuclear and renewable energies are both 1 to 2 orders of magnitude less carbon intensive than fossil fuels. So the sorts of energies that we're looking to transition to. About abundance, nuclear and renewable energy can't replace fossil fuels today with their current technology. One problem is form, and that is that nuclear can't power uranium mining, for example, much less like these technologies, nuclear and renewable energy, are mostly in the form of electricity, and that can't power aviation and a bunch of other long-distance transportation, at least right now. And then there are emerging uses of those sorts of energies to power all sorts of, there's people coming up with solutions for all these problems, but they're all running into scale right now. Like, I mean, of course, like you can use wind energy to power ships across the ocean with sails, but it can only go so fast. You can, power factories, as was done a lot a couple 100 years ago with the energy from river, like run-of-river hydropower, but there's only so many factory sites along strong rivers, for example. So right now, what it looks like is nuclear and renewables both providing very small portions of total energy, other than biofuel and waste combustion mostly for direct heating and cooking uses. So since nuclear energy first became a thing back in the 40s and 50s, when folks got excited about nuclear weapons and nuclear energy at about the same time, there have been predictions that we're going to have a nuclear-powered, super-abundant society very soon. And it's not for lack of trying that hasn't happened. Actually, between 1948 and 2014 in the US, research and development from the US government toward energy technologies, 50% of the money went to nuclear, and the rest was split between fossil fuels, renewables, efficiency. Now nuclear still gets about 25% of energy R&D from the US. These numbers are similar. Across the entire OECD during the 70s, 75% of energy R&D investment went toward nuclear. So now people are saying the same thing about renewables. They're saying soon all the problems that we have with renewables can be solved, they can be scaled up, and the difference between renewables and nuclear is nuclear, it's been tried, and renewables are still in the nascent stages. We don't know, but the renewables, the 100% renewable energy society advocates who think that there's no decrease in energy use that needs to happen at all, their claims sound very similar to the people talking about nuclear energy in the 1950s. As far as expense goes, I should probably speed up a little bit, so I want to clear enough time to talk to. This, from the ecological economic perspective, this is hardly worth looking at because cost is a social construct and only sort of reflects an underlying material reality. And it's interesting to know that nuclear prices have gone, the cost of constructing nuclear power plants has gone up over time, and the cost of wind energy, solar photovoltaic, and other renewable energies is going down really, really rapidly right now. But again, the real limits are biophysical, and as Ben was saying, ecological economists like to use, when discussing whether energy sources, how expensive they are, like to use energy returns on energy investment. And so, like with carbon emissions, or maybe more so, it's very hard to calculate energy returns on energy investment. There's not a lot of consistency between studies. There's also not a lot of funding to study this. So it's hard to get good numbers. The idea is that society needs an energy return of greater than 1 and probably greater than 2 or 3, because you also have to have energy to build the infrastructure to consume energy and build houses and stuff. So, not 5 minutes left. The point of this one is that the energy return on energy investment goes down over time. You use the good stuff first, and that applies to fossil fuels. Like now we're scraping the bottom of the barrel, they say, using unconventional forms of fossil fuels, and energy return on investment has gone down from over 100 for oil to now in the US it's in shale oil and tar sands in Canada, under 10 in a lot of cases. And it'll go down for nuclear too, because there's limits to the amount of extractable uranium. It'll go down for wind and solar because the best sites only exist. And you can only build wind turbines on them once. You can only have one layer of solar panels on the best sites. So energy returns will get lower over time. As far as safety goes, these are the ones that are really interesting to talk about. Nuclear energy is made by fissioning radioactive materials, and that fissioning creates energy and tons more radioactive materials, and those have to be kept separate from humans forever, basically. Tens of thousands of years, perhaps, depends on the level of safety. The nuclear waste problem is a big one because of the fact that even if you had a good way to communicate to humans really, really far in the future that there's something unsafe here, the history of tomb raiders and archaeologists shows that humans ignore those warnings and go dig it up anyway. Accidents are really hard to have frequencies. Lay people tend to overestimate accident frequencies, but their estimates are actually closer to actual accident rates. Their estimates are closer to actual accident rates so far than the expert risk assessments. If you see, so far we've had two really major accidents, Fukushima and Chernobyl, over 17,000 reactor years. If you were to scale up nuclear energy to say 12.5 terawatts to power the world, you would need 12,501 gigawatt nuclear reactors, and you'd be looking at in any given year, about a 75% chance of an accident that big if you assume that accident rates stay about the same. Small accidents are happening all the time, these near misses, and if you do the complicated math about accident frequencies and sort of find statistical regularities that scale up, which people have done, it shows about the same results in that accidents in a very scaled up nuclear world. And then weapons, nuclear energy, nuclear weapons are about the same technology, so if you're going to spread nuclear energy technology all over the world, there's all these weaponizable materials that get out. This is what I like to talk about the most, but maybe it's the least relevant to the biophysical economics part. So I'll leave it at that. People perceive risks. Experts often say that people are irrationally afraid of nuclear energy because fossil fuels actually kill more people, and renewable energies even kill more people per kilowatt hour or terawatt hour. But how people die matters too, not just sort of. And there's no big accidents that have ever been created by renewable energy technologies. So the public's assessment is valid, is basically the point that I want to make there. How we feel about nuclear energy is valid. And then a lot of people really like nuclear energy instead of renewable energy because for a high energy consuming society, it's dense. It can create power without taking a lot of land, transforming a lot of ecosystems to like very constructed systems, unlike solar panels covering the desert with them and stuff like that. Wind energy actually has a pretty high power density. When you look at just the built infrastructure, it has to be spread out over a large space. But to focus on these, energy systems cover about 1% of the world or less. It's energy consumption systems that cover all the world, because when you produce energy, it gets consumed. And when you have more and more powerful energy sources, humanity so far has taken full advantage of that. And I just want to finish up by saying that energy use has grown and grown and grown, and coming up with substitutes for different energy sources has never decreased the use of those energy sources that were supposed to be substituted. So there's nothing deterministic technologically about having the substitutes around. Yeah, I'm out of town, and I want to leave time for Claire. But anyway, to conclude, basically, using the principles of ecological economics and the tools that ecological economists have to assess energy sources, there's a really strong argument to be made against nuclear power for climate change. Thank you.